Hi everyone. So we have been studying about operation and amplifier. So we have seen different configuration of OpAmp. In the previous video, we saw the configuration of non-inverting amplifier and inverting amplifier. We saw that in a very depth manner. We saw everything about that. We also saw how to analyze it when there is a non-ideal OpAmp. Right. So same thing we are going to do with the voltage follower circuit. Why it is called voltage follower? Because output is directly proportional to the input. Not directly proportional. Output is equals to the input. Right. So let's just consider this is an ideal op amp. So what will be the voltage gain of this? Tell me what will be the voltage gain? Voltage gain. I am finding voltage gain. What will be the voltage gain? Since there is a negative feedback, involved. So positive terminal potential and negative terminal potential will be equal only. So this potential will be equals to Vi only. So V naught is equals to Vi. So here the voltage gain is 1. Right? Voltage gain is 1. Very easy because output is equals to input only. That's why it is called voltage follower. That's why it is called, this configuration is called voltage follower. Quickly tell me what will be the input impedance? What will be the input impedance? R in. V in by I in. What is the value of V in by I in? What is the value of I in? I in is 0. I in is 0. So R in would be infinity. And quickly tell me what will be your R out? What will be your R out? So for R out, what you will do? You will short circuit the input. You will short circuit this. If it is shorted, then here there will be 0 volt only. That means V naught is becoming 0. So R out is V naught by I out. This will be your I out. Right? But your V naught is 0 only. Since input is shorted, so this is coming towards output only. So R out is 0. Well and good. Very easy. Now we will do the same thing with respect to non-ideal op amp. So before analyzing the circuit, tell me what kind of feedback topology is there? What kind of feedback topology is there? Is there current mixing? No, there is voltage mixing. There is voltage mixing. Certainly there is no current mixing, so there is voltage mixing. What about sampling? The voltage V naught is directly coming towards the input side. Voltage V naught is directly coming towards the input side. So certainly there is voltage sampling. Voltage sampling. So what kind of feedback topology is there? Voltage feedback topology. And if it is voltage feedback topology, what do you understand by that? That it is a voltage amplifier. It is a voltage amplifier. So across a voltage amplifier, there is a feedback connected that is making it to a voltage amplifier only. So we can write down the expression directly. What will be your voltage gain? Tell me. What will be the voltage gain? If the gain A here is, if the gain here is A, so what will be the voltage gain? A upon 1 plus A beta. A upon 1 plus A beta. What is the feedback factor here? What is the feedback? This is the feedback, right? This is your feedback. This is the feedback. Say yes or no. From output, how much portion is coming? That is called feedback. What is the feedback factor here? Feedback factor is 1. Because output is directly coming. When we studied non-inverting amplifier, what was the feedback factor? This was the scene. This was your V in. This was the resistance. This was your V naught. This was your R2. This was your R1. Then we said our feedback factor is beta, that is R1 upon R1 plus R2. This is what we said, right? Because from output R1 upon R1 plus R2 portion was coming. R1 upon R1 plus R2 into V naught. That was your V feedback. So what was your feedback factor? This R1 upon R1 plus R2. But here the feedback factor is 1. Completely output is coming. So feedback factor is 1. Feedback factor beta is equals to 1. So tell me what will be the voltage gain? First thing, what will be the voltage gain? Voltage gain is going to be A upon 1 plus A beta, where beta is 1. So it will be A upon 1 plus A. What will be the input impedance? Input impedance. Input impedance would be R in into 1 plus A beta, because for a voltage amplifier, input impedance is larger. For a voltage amplifier, input impedance is larger. Why so? Because you want more and more voltage across the input impedance. So input impedance is larger. So 1 plus A beta, beta value is 1. So Rin into 1 plus A. And what will be the output impedance? For a voltage amplifier, output impedance is low or high? The output impedance is low. For a voltage amplifier, output impedance is low. So what will be your output impedance? That would be R naught into 1 plus A. Sorry, R naught by 1 plus A. R naught by, since it is less, so I will be dividing it. R naught upon 1 plus A beta, where beta is 1. So R naught by 1 plus A. That's it. So this is how you can directly write, or you can derive as well. So let's derive it now. We can derive as well. So we can derive one by one. So this is the last time I am deriving it. Otherwise you can write it on your own as well, right? Also you can derive it on your own as well. So again, let's just derive the expressions for voltage gain. You can quickly skip it, or you can quickly watch me doing it, and here in your preparation you can save your time. Like, you know the derivation, you also know that you can do it on your own as well. So why you should watch me doing it? You should be quickly skipping it and doing it on your own. That's it. It will help you in practice as well, and also it will improve your concept. Also it will save your time. So V naught is coming. So what will be your V naught? V naught would be A into V in minus V naught, because I told you when I am writing the voltage gain, I am going to ignore R in and R naught. R in will be infinity, R naught will be 0 when I am writing the voltage gain. So your V naught will be simply A upon 1 plus A. That's it. Without even drawing the internal structure, I could write the gain. This was the voltage gain. What about the input impedance? What about input impedance? So for input impedance, this V naught is traveling here, and here there is Rin, right? Here there is Rin. This is your Rin, and this is Rin with feedback. I should write Rin with feedback and R naught with feedback. So Rin with feedback, what it will be? Rin with feedback, that would be V in by I in. My target is to find V in by I in. You have already seen the derivation for the non-inverting amplifier, so it should be easy for you. So my target is to find Rin with feedback. Rin with feedback, that would be V in by I in, right? So Rin is connected to two nodes. This is your Rin. In the internal structure of OpAmp, this is your Rin. This node is V in, this node is V naught. This is your Rin, and from here there is current. This is the current, which is I in, right? So what you can write? V in minus V naught is equals to I in into Rin. Say yes or no? And what is V naught? Here it will be V. What is V naught? V naught is A upon 1 plus A into V in is equals to I in into Rin. So from here you can directly see that your Rin with feedback will be Rin into 1 plus A. That's it. What about output impedance now? You have to find output impedance considering the non-ideal op amp. For output impedance, we always make an assumption. What is that assumption? For output impedance, I think I should make the internal structure as well. So how will the internal structure look like? This is your Rin, which is of no use actually, and this V in is shorted because I am calculating R out. So V in is shorted. This V in is gone. This node is already V naught. This node is V naught only, and here it will be amplified with the factor of A. Will be amplified with the factor of A. So V naught minus 0, it would be minus A V naught. Say yes or no? Because here you are having V naught. So this negative terminal is at V naught potential. So A into 0 minus V naught, it would be minus AV naught. And here there is R naught. That's it. So you need to calculate your R out with feedback. R out with feedback from here. So your target is to find V naught by I naught. But what is the assumption we take? The assumption we take is that the complete current will be flowing through R out. Because R naught is very low, so complete current will be flowing through R out. Now people will say, sir, why you are taking this assumption, sir? This is a short circuit path. So all the current should flow from this short circuit path. No, this is not short circuit path. In this path there is Rin connected as well, which is very high. So that's why current is not trying to flow from here. The current is flowing from R naught. It's not that you only see this path. This is short circuit path. No. This is not the short circuit path. There is Rin connected as well. So I naught is completely flowing through R naught. So V naught minus of AV naught divided by R naught is equals to I naught. So your V naught by I naught, that would be R naught upon 1 plus A. So your R naught with feedback is R naught upon 1 plus A. So this is how you can derive, or if you have a good idea of feedback topology, then also you will be able to derive within seconds only. You will be able to write down the final answer within seconds only if you have good idea of feedback topology. With the concept of feedback topology, we wrote the voltage gain, we wrote the input impedance. That was very easy because input impedance will be high and output impedance will be low. So this is how we could write, and feedback factor was 1 here. Very easy, everything is crystal clear, there is no doubt about it. Well and good. Let's see some application of the OpAmp. So we can use the OpAmp as a adder, subtractor, as a multiplier as well, as a divider as well. So all those things we are going to see now. How we will use it as a multiplier, how we will use it as a adder, as a subtractor. So first let's just see how it is working as a adder. Now here it is written inverting adder. Why inverting adder? Because inputs are applied at inverting terminal. These V1, V2, V3, these inputs are applied at inverting terminal. So that's why it is called inverting adder. So what will be the output? You can directly write the output. This node is 0, so this node will also be 0. So what will be the output? Here I am applying the nodal analysis at this point because the input current is 0 ampere. Input current is 0 ampere. So what will be your output voltage? 0 minus V in by R1 plus 0 minus V2 by R2 plus 0 minus V3 by R3 plus 0 minus V naught by RF. RF is equals to 0. So what will be your V naught? V naught will be minus 1 by RF, V1 by R1 plus V2 by R2, sorry, minus RF, not minus 1 by RF, it would be minus RF plus V3 by R3. And if R1 equals to R2 equals to R3 equals to R, if R1 is equals to R2 is equals to R3 is equals to R, then what would have happened? If all are equal, then what would have happened? V naught would be equals to minus RF by R into V1 plus V2 plus V3. So you can adjust your RF and R value and you will get the addition at the output. But there will be a negative sign. The sign will be negative there. Why there is a negative sign? What does that negative sign show? That your input are applied at inverting terminal. So this is known as inverting adder. So very simple, I just apply the concept of nodal analysis. 0 minus V1 by R1, 0 minus V2 by R2, 0 minus V3 by R3 plus 0 minus V naught by RF. So for V naught value is minus RF into V1 by R1 plus V2 by R2. Very, very easy. Well and good. Let's see non-inverting adder. Why it is non-inverting? Because your input are applied at non-inverting terminal. And you can take the condition that already the condition is given, that is R1 is equals to R2 is equals to R. Okay. So what I am going to do, I will assume this node is V. If this node is V, then what will be your V node? If this node is V, this node will also be V. Right? If this node is V, that means there is V by R current here. If there is V by R current here, the same current will be flowing here because here there is 0 ampere current. So this same V by R current is flowing in this direction. If the V by R current is flowing in this direction, so this is giving you a drop of this much in this direction. So V by R into RF. So what will be your V naught? Your V naught will be V plus V by R into RF. So your V naught will be 1 plus RF by R into V. Right? This is equation 1. Also, you did not need to do all those things. Why so? Because I already told you, you have to remember the formula of non-inverting amplifier gain. What is the gain of non-inverting amplifier? 1 plus RF by R. The input was at this terminal. For that formula that we remembered, the input was there at this terminal. So at this terminal, input is there. The input is V. So what will be V naught by V? V naught by V would be 1 plus RF by R. This is how you can remember. Say yes or no. I told you to remember the formula for this configuration. This node is your V in, and then there is a feedback involved. This was your V naught, and this was your RF, this was your R, and this was grounded. So I told you to remember the formula 1 plus RF by R into V in is equals to V naught. The same thing, 1 plus RF by R into V is equals to V naught. So directly you could write down if you have remembered the formula. And slowly we will be using it a lot of times, so you will be able to remember it. Now your target is to find the potential V. So here there is 0 ampere current. So what will be your potential V? Tell me. V minus V1 by R1 plus V minus V2 by R2 plus V minus V3 by R3 is equals to 0. V minus V1 by R1 plus V minus V2 by R2 plus V minus V3 by R3 is equals to 0. Now we can take R1 equals to R2 equals to R3, and if we don't take the, if I don't take this condition, then the expression will be a bit complex. Expression will look something like this. R1 plus V2 by R2 plus V3 by R3. Then you can take the value of V from here and replace it here. That would be your final answer. But the expression will be a bit complex. So what I will do, take R1 equals to R2 equals to R3 equals to R. Right? So it would be 3V by R plus V1 by R plus V2 by R plus V3 by R. So from here you could get to know that your V is equals to V1 plus V2 plus V3 by 3. Simple mathematics is there, just simple network analysis we are doing, nothing else. We found the value of V, that would be V minus V1 by R1 plus V minus V2 by R2 plus V minus V3 by R3. So V into 1 by R1 plus 1 by R2 plus 1 by R3 equals to V1 by R1 plus V2 by R2 plus V3 by R3. So all R I am taking equals to R, so that there is a easier calculation. So if all R equals to R, so V1 plus V2 plus V3 by R, and here it would be 1 by R plus 1 by R plus 1 by R, that would be 3 by R, so 3V by R. So V value you are getting is V1 plus V2 plus V3 by 3. So this you can replace here now. By equation 1 and 2, what you will get? V naught equals to 1 plus RF by R into this V potential. What will be V potential? V potential will be V1 plus V2 plus V3 by 3. Now if you need V naught equals to V1 plus V2 plus V3, what you need to do? We just need to put if RF is equals to 2R. If RF is equals to 2R, then what will happen? If 2R is there, so this will become 2, 2 plus 1, 3, and 3 and 3 will get cancelled. So V naught will be equals to V1 plus V2 plus V3. That's it. If R is equals to 2R, then. Well and good. So these kind of configuration will be given, and they will ask you what will be the final output voltage. So any kind of configuration can be there, any kind of gain can be there. So you just need to apply network analysis and get to the final answer. In the next video only, we will be solving a lot of assignments. So there you will be very much comfortable with these kind of questions, right? Now we are going to study about differential amplifier. So basically in the output you will have V naught into some gain, and then these subtraction of these two potential, VA minus VB. Some people call it subtractor as well, subtractor. So in the output, what you are going to have, some gain into VA minus VB. This is what differential amplifier is. Difference of the voltage that we have applied. So in the output, we need difference of the voltage that we have applied. Well and good. So they are saying take R1 equals to R2 and RF equals to R3. So better it should be written like this. The ratio should be same. I don't need the same values, I need the same ratio. R1 by RF should be equals to R2 by R3. This should be given. In most of the questions, this ratio will be given, that your R1 by RF is equals to R2 by R3. This you need to take. So let's analyze this circuit. So how we will analyze when there are input at both of the terminal, at inverting terminal as well, at non-inverting terminal as well. There are inputs at inverting terminal as well. This is inverting terminal, so input is there as well, right? And input is there at non-inverting terminal as well. So if this is the condition, I generally prefer applying superposition theorem. So first I will consider only VB, and then I will consider only VA, and then I will see. Okay, so I will apply superposition theorem. Copy this circuit, and then I will apply superposition theorem. Applying superposition theorem. First I am going to consider only VA. Considering only VA. If I am going to consider only VA, then this will be certainly gone. This will be shorted. I hope you know superposition theorem, that you must have understood in basic network analysis as well, right? So what will be this node? Let's just say this node is V. So what will be your V node? This V node I will be calling V node A. Why so? Because this is not the final output, because we are applying the superposition theorem. So first we are considering only VA, so I am calling this output as V node A. So what will be your V node A? Your V node A will simply be, if this node is V, if this node is V, so what will be your V node A? 1 plus RF by R into V. Say yes or no? Say yes or no, right? This I am calling equation 1. And what is the potential of V? Potential of V is R3 upon R3 plus R2 into VA. Say yes or no? Why is it so? Because here you can directly apply the concept of potential divider. Here you can divide the potential, because here there is 0 ampere current. Here there is input current is 0 ampere. So directly the configuration is looking something like this only. This is how the configuration looks like. This is R2 and this is R3 and this is VA. So you are just finding the potential V here, that is equals to R3 upon R3 plus R2 into VA. That's it. Okay, so by equation 1 and 2 you can write down the value of V naught A. So what will be your V naught A? Your V naught A. Your V naught A would be 1 plus RF by R1. 1 plus RF by R1 into R3 upon R3 plus R2 into R3 upon R3 plus R2 into VA. This is your V naught A. Now secondly, now we are going to consider VB only. So if I am going to consider VB, what will happen? This will be gone. I am only considering VB. Now tell me, if this is gone, then R2 and R3 are coming in parallel. R2 and R3 are coming in parallel. I can replace R2 like something like this. What is the current here? 0 ampere. Now the same current will be flowing through R2 and R3 parallel combination as well. This is the parallel combination of R2 and R3. So I can simply replace this as one resistance only, and that would be R2 parallel with R3. Say yes or no? What did I do? First I short circuited VA. If I short circuit VA, R2 and R3 are coming in parallel, so I replaced it with one resistance only. Now in this resistance there is 0 ampere current. If there is 0 ampere current, that means there is 0 voltage drop across this resistance. There is 0 voltage drop. So this node is 0. The ground node is 0 and then there is a 0 voltage drop. So this node will also be 0. So basically this node will be grounded only. So the complete configuration can be replaced something like this. Just a ground. Look, what was the scene? This was the circuit. I short circuited VA. If I short circuit VA, what will happen is that R2 and R3 will come in parallel. But R2 and R3 has 0 ampere current. If both are having 0 ampere current, that means they will give 0 voltage drop. So here the voltage drop was ground. So this ground will be carrying here and it will be becoming ground only. So this V positive node has become ground. This node has become ground. Now if this is grounded, then this will also be grounded. So what is V node by VB? You can calculate it or you remember this formula, because this is the formula of inverting amplifier. What is the formula of inverting amplifier? This I am calling V node B. So what will be your V node B? V node B would be minus RF by R1 into VB. That's it. This is your V node B. So this is equation 3 and equation 4. So what will be your final V node? Final V node will be V node A plus V node B, and that would be 1 plus RF by R1 into R3 upon R3 plus R2 into VA minus RF by R1. Simply I am adding it, minus RF by R1 into VB, right? So this is the V naught expression I am writing. Now I need to make it better. How will I make it better? Because I have the ratio. What is the ratio given to me? The ratio given to me was that your R1 by RF is equals to R2 by R3. R1 by RF is equals to R2 by R3. Given R1 by RF is equals to R2 by R3. This is given. So R2 by R3 I can replace it with RF by R1. Okay. So what is the relation I am getting? That is 1 plus RF by R1 into R3 upon R3 plus R2. This is what I was getting. R3 upon R3 plus R2. So what I will do, I will keep this R3 downward. I will take this R3 downward. So 1 upon 1 by R3. So R3 by R3 would be 1. So it would be 1 plus R2 by R3. Are you getting this point? How did I write it? I took the R3 downward. So it would be 1 plus R2 by R3. So 1 plus R2 by R3 can be replaced with R1 by RF. Say yes or no. It can be replaced with R1 by RF. That we will replace in the next expression. So into VA minus RF by R1 into VB. Right? Now this expression I can write R1 plus RF divided by R1. Right? 1 upon 1 plus this R2 by R3 can be replaced with R1 by RF. So if I am replacing with R1 by RF, so what it will be? This RF will go upward and it will come here as well. Basically the expression is 1 plus R1 by RF. So what I can write? RF upon RF plus R1. Say yes or no. Right? This RF will go upward, RF plus R1. Simple mathematics, nothing else. So it would be RF is going upward and RF plus R1. VA minus RF by R1 into VB. So this is getting cancelled. So what you are getting in the output? RF by R1 into VA minus VB. This is what you are getting at the output. That's it. Say yes or no. So with the whole calculation, this was the circuit given and the final output we could write. So what you need to remember in this differential amplifier? So if it is possible for you, then you should remember the final expression. The final expression we got is this. This you can derive it on your own as well with your simple calculation. This was just the calculation, nothing else. First I consider VB, then I consider VA. Sorry, first I consider VA only. If I consider VA, then I could apply the superposition. I could apply the voltage. voltage division. If I could apply the voltage division, then I could write the gain as well. So R3 upon R3 plus R2 into 1 plus Rf by R1 into Va. That was the first gain, and then considering Vb, what was the gain? Minus Rf by R1 into Vb. So this was the final expression. I had the expression, I had some ratio given, this was given, this ratio was given, then I replaced the values and got to the final answer, that was this. So what was your circuit? This was the circuit. This was the circuit. So I am writing as a conclusion. So if you can remember, you should be remembering it. What you need to remember? That ratio from here to here and here to here is the same. Ratio from R1 by Rf and R2 by R3. If it is same, that if R1 by Rf is equals to R2 by R3, then what will be your V0? V0 will be Rf by R1. You just need to see here, that's it. So your V0 will be Rf by R1 into potential of positive terminal Va minus potential of negative terminal Vb. That's it. Ratio of these two divided by Va minus Vb. So this is how you can remember that this ratio to this ratio should be equal. Rf by R1 should be equal to R3 by R2. If that is equal, then this would be the answer. Rf by R1 into Va minus Vb. This you can encounter in a lot of question. If you remember this, your calculation will be reduced. A lot of times your calculation will be reduced. So if you are able to remember it, that would be very good. So this was the differential amplifier. Your target was to get the output that should be proportional to the difference of both of the input. So here your output is proportional to the difference of both of the input that you applied, that is Va minus Vb. Say yes or no. Is it so? Right? Well and good. So this was the differential amplifier. Now we are going to study about instrumentation amplifier. Why it is called instrumentation amplifier, what is the advantage, everything we will see. But let's just analyze it. Let's just find the output voltage first. So our target is to find the output voltage first. This is our target is. So what will be the output voltage? Can you tell me? Let's just assume if this node is your V2 and this node is V1. What will be the output voltage? Can you tell me? If this node is V2, this node is V1, what will be the output voltage? In terms of V2 and V1. In terms of V2 and V1, you need to tell me. You can tell. You have already seen it. This portion, this much portion is a differential amplifier only. R1 by Rf, R1 by Rf. Look, these two resistance, these two resistance. These two resistance and these two resistance. One resistance is in feedback, one resistance outward. One resistance is feedback, one resistance is outward. Two resistance connected to one of the input. Two resistance connected to one of the input. Same. This is a differential amplifier only. And the ratio is also same. R1 by Rf, R1 by Rf. So what will be your final output? Rf by R1, Rf by R1 into potential of positive terminal, potential of positive here, V1 minus potential of negative V2. This is potential of negative V2. Right. So this will be your final output. This equation 1. So now your target is to find V2 and V1 in terms of Vx and Vy. That's it. So if this node is Vx, this node will certainly be Vx. If this node is Vy, this node will certainly be Vy. Say yes or no. Very easy. If this node is Vx, this node will be also Vx because there is a negative feedback. If this node is Vy, this node will also be Vy because there is a negative feedback. That's it. Very easy. What is the current here? The current here would be Vx minus Vy by Rg. Say yes or no. Now the same current will be flowing through R2 and the same current will be flowing through this R2. Say yes or no. The same current will be flowing in the complete ladder. Why so? Because this is driving 0 ampere current. This is driving 0 ampere current. This is also driving 0 ampere current. The input of OpAmp drives 0 ampere current. So this is the input of the OpAmp which is driving 0 ampere current. This is also driving 0 ampere current. So whatever the current is flowing, that same current is flowing through R2 as well. Say yes or no. Everything is crystal clear. So in the complete branch, Vx minus Vy by Rg current is flowing. So what will be the potential V2? what will be potential V2? So can I write potential V2 will be Vx plus, potential V2 will be Vx plus potential across this resistance. What will be the potential across this resistance? That would be R2 into the current. R2 into the current. What is the current? Vx minus Vy by Rg. Vx minus Vy by Rg. This is your V2. What about V1? So what will be your V1? This is your Vy. Vy minus Vy minus, why minus? Because Vy and this potential will be subtracted. The potential across R2 will be subtracted from Vy, so you will get V1. So Vy minus this resistance R2 into the current. What is the current? This is the current. Vx minus Vy by Rg. Say yes or no. This is equation 3. So what will be your final output voltage? Your final output voltage will be Rf by R1 into V1 minus V2. What is V1? Vx plus, what is okay, V1? V1 minus V2. So Vy minus R2 by Rg into Vx minus Vy minus Vx minus R2 by Rg Vx minus Vy. Right? Everything is crystal clear. So Rf by R1. What do I actually need? Vy minus Vy. Okay, so what I am going to do, this is Vy, this is Vx. So Vy minus Vx I am taking common here. Vy minus Vx. Now I am taking minus common from it. So what I will get? Plus R2 by Rg Vy minus Vx, and the same thing I am going to do with this one. What it will give me? Plus R2 by Rg Vy minus Vx. Right? So from the complete expression I can take Vy minus Vx common. Vy minus Vx, Vy minus Vx, Vy minus Vx. So Rf by R1, and I am taking Vy minus Vx common. So what it will be? 1 plus 2R2 by Rg. 1 plus 2R2 by Rg and Vy minus Vx. That's it. This is your final V note. So sometimes directly this expression is asked, that what will be the output voltage, and the same kind of expression they will give, the same kind of resistance value they will give, and you will be able to write down the final answer. How will you write down? V1, V2 you already know, then you know the final output potential as well. If you know the final output potential, then your target is to find V1 and V2 potential only. Then you can write down, or else you can remember it as well, because this much of expression you already remember. Rf by R1 and this much of expression you already remember. Just this is added. So how will you remember it? Let's write down at a note. Just write it down as a note. You will be able to remember, that's my guarantee. No issue about it. How will you remember? So these kind of things you can just write it on a paper and should revise daily, because these will reduce your calculation. If I am asking you to remember anything, believe me, it is only for the calculation purpose, that your calculation will be reduced. Otherwise you can derive the same thing in the examination. It will take very less time if you forget it. But if you are remembering it, it will be very easy. And how will you remember? If you solve the problems. The as much problem as you solve, it will be clear in your mind for a longer time, right? So all those things I am not going to write. I am just writing the conclusion. What do I need to remember? So conclusion. What is my V note? So first thing I will see here, this and this ratio same. Okay. Then Rf by R1. Very good. Then I will see this is an instrumentation amplifier. So R2 is there for 2 times. R2 is there for 2 times. So what I am going to write, 1 plus 2R2. Rg is only for one time. The common resistance, the resistance which is common, that is already there for one time only. So I am writing it for one time only, Rg. R2 was there for 2 times, so I wrote it 2R2. So Rf by R1 into 1 plus 2R2 by Rg. Potential at positive terminal minus potential at negative terminal. So this positive terminal is connected to this potential, because what is happening is that this Vy is coming here. So Vy is near to this positive, and this Vx is coming here. So this Vx is near to this negative. So this is how you can remember. So Vy positive potential minus negative potential. That's it. This is your final answer. This was for instrumentation amplifier, and for differential amplifier this was the answer. Rf by R1 into positive potential minus negative potential, Va minus Vb, and here Vy minus Vx, positive potential minus negative potential. So what did you understand here? Isn't it the same as differential amplifier? So instrumentation amplifier is a kind of differential amplifier only, because what differential amplifier was doing, it was amplifying the difference of the input applied. Difference of the input applied. What was the input applied here? V and Vb. What is the input applied here? Vx and Vy. So it is amplifying the difference of input applied. That's it. So here also V0 is proportional to Vy minus Vx. It is amplifying the difference of applied input. Difference of applied input. And it is amplifying that. But in the differential amplifier, what was the amplifying factor? In differential amplifier, what was the amplifying factor? That was Rf by R1. In differential amplifier, that was Rf by R1. What is the amplifying factor here? Rf by R1 into 1 plus 2R2 by Rg. Which is larger? Say yes or no. So what I am going to write, instrumentation amplifier is a kind of differential amplifier with higher gain. That's it. Now where do we use instrumentation amplifier? What is the advantage of an instrumentation amplifier? Let's see that. So we have a high gain here and high input impedance. Oh, that was a very interesting thing. I forgot to write down the input impedance value. So let's write down the input impedance value for differential amplifier. So I need to add a slide. Input impedance we forgot to discuss. Input impedance of differential amplifier. This we need to discuss now. So you guys only will tell me what is the input impedance of differential amplifier. What do I mean by input impedance? I mean the resistance looking from here. What is the impedance? What I will do, I will apply a battery. So I will apply a battery of Vi between these two terminals. I need the impedance between these two terminals, because here there are my input, no? My input are here and here. So I need the impedance between these two terminals. This is Vi and we are getting II out of it. Tell me one thing, this Vi is getting out of this II is getting out of this Vi. So it should be getting into it as well. That's for sure. So through this R1, if II current is flowing, then it is certain that through this R2 II current would be flowing. Because there is a battery, simply this is the scene, that there is a battery Vi, from it some current II is going, and then there is a resistance connected R1. There is further circuitry, we will talk about it, and then there is this resistance R2 as well. So this current II has to flow from here, and this current II is going in here, so it has to flow from here as well. Say yes or no, right? So this you agree. Now these nodes and these nodes, these two nodes are virtually shorted. Say yes or no. these two nodes are V negative and V positive node. These two nodes are virtually shorted. So isn't it becoming a closed loop? So what is the impedance in the closed loop? Both of the resistors are having the same current. So the impedance is R1 plus R2. That's it. These two nodes are virtually shorted. If you don't understand by that, let's just assume the potential of this node is Vx and potential of this node will also be Vx. If this is Vx, this node will also be Vx. So let's write down KVL equation. Let's write down KVL. So this node is Vx. So what I can write? Vx minus I in R2 plus V in minus I in R1 is equals to Vx. I started from here. This was the voltage drop across R2. This was the voltage drop across R1. So I started from here. Vx minus I in R2 plus V in minus I in R1 minus I in R1 is equals to Vx, is equals to this node, is equals to Vx. So Vx and Vx are getting cancelled. So what you are getting? V in is equals to I in into R1 plus R2. So what is your V in by I in? That you are calling R in. That is equals to R1 plus R2. What is the input impedance? That is equals to R1 plus R2. For a differential amplifier, input impedance is R1 plus R2. You can remember it like this as well, that these are virtually shorted. So R1 plus R2 both are coming in series only. That's it. Or you can, if you are not satisfied with that explanation, then you can apply the KVL as well. So if you apply the KVL, you get to know that your resistance is R1 plus R2. What is the input impedance of instrumentation amplifier? Input impedance of instrumentation amplifier. Impedance of instrumentation amplifier. This was your instrumentation amplifier. You can directly tell me, it is clearly visible. What is the answer? Answer is infinity. Why is it so? Because what I will do, I will apply a battery of Vxy here and get current out of it. And what is the current getting out of it? That is equals to 0. This I can apply, or I will call it V in. Better, let's just call it V in and get I in out of it. Since there is OpAmp connected directly, so OpAmp will drive 0 ampere current. So what is your R in? R in is looking from here. This was your R in. So R in will be V in by I in. V in by I in. What is I in? I in is 0. So R in will be infinity. So in instrumentation amplifier, there is a very high input impedance. So for a voltage amplifier, what is the requirement? All these are voltage amplifier only, because what is the input? Input is voltage, output is voltage. So these are voltage amplifier. So what is the requirement for a voltage amplifier? You need high input impedance or low input impedance? You need a high input impedance. So instrumentation amplifier is a better amplifier because it is having high input impedance. It is also having higher gain as well. So it has high gain, high input impedance and high CMRR. We will discuss about it, but later on when we study about the offset and all those things, we will certainly discuss about it. Just wait for 4 to 5 lecture. We will certainly discuss about it, why instrumentation amplifier is having high CMRR, what is the meaning of CMRR, how to calculate CMRR. We will discuss about it, but you have to wait. Well and good. The gain of instrumentation amplifier is this 1 plus 2R2 by RG, RF by R into V positive minus V negative, and the gain of differential amplifier is RF by R, V positive minus V negative. So what are the advantage of instrumentation amplifier over differential amplifier is that higher gain, higher CMRR, higher input impedance, and you have a more control over gain. What do I mean so? What do I mean by that? You have more control over gain. Look, what did I tell you? In differential amplifier. In differential amplifier, what did I tell you? That this ratio R1 by RF should be same as R2 by R3. Then only you will get this expression, right? R1 by RF should be equals to R2 by R3. Let's just say for increasing the gain, I need to increase the gain. Let's just say my target is to increase the gain. So what I will do, I will increase this RF value, right? RF value I will increase. If I am increasing this RF value, then certainly I have to increase R3 value as well. Say yes or no. Because there is a condition that you need to maintain the ratio. So if I need to maintain the ratio, to increase the gain, I need to increase RF, then I need to increase R3 as well, right? Understood? But in case of instrumentation amplifier, what is the scene? In case of instrumentation amplifier, this is the gain, Rf by R1, Rf by R1, 1 plus 2 R2 by Rg. So here this ratio has to be maintained. Yeah, that's for sure. But if I need to increase the gain, I am not going to change these two values. No, I am not going to change these two values. What I am going to change? I am going to change this Rg value. I will increase this, no sorry, I am going to change this R2 value. I will increase this R2 value. If I increase this R2 value, my gain will increase. Say yes or no. So there is no issue of changing other resistances. Are you getting this point? Or I can decrease my Rg value. If I need to increase the gain, I can simply decrease my Rg value by only controlling one resistance. This resistance is generally controllable. So by reducing the value of Rg, what I am doing? I am increasing my gain. So there is more control over the gain. In the differential amplifier, if I change this one, I have to change this one as well. Why so? To change the gain. But here in the instrumentation amplifier, if I need to change the gain, I don't need to change these two values. I am not changing these values. I am only changing Rg value. Just by changing Rg value, my gain will change. Say yes or no. So you have more control over gain in case of instrumentation amplifier. So more control over gain by changing less resistor values. So only one resistor value I had to change here and I could change the gain. Say yes or no, right? Now what is the use of instrumentation amplifier? So there is something called transducer. So those students who are from instrumentation engineering, they will be studying about sensor and transducer. So what transducer does is, it will take some physical quantity, let's just say temperature, or it can be pressure, or it can be any quantity. So it will take some form of energy and it will convert it into electrical signal, some form of energy to electrical signal. Let's just say there is a change in temperature. So what it will do, it will convert this change in temperature to electrical quantity, let's just say some millivolt. So if your temperature is changing by some 10 degrees Celsius, so in some oscilloscope you will get some millivolt output. If your temperature is changing by 10 degrees Celsius, in the oscilloscope you will get some 10 millivolt output. If your temperature is changing by 20 degrees Celsius, in the oscilloscope you will get some 30 millivolt output. So this is what transducer does. Okay. Now the output that we get from the transducer, that is of very, very small magnitude. It will be of microvolt or microampere. Now if that is a very small signal, then the oscilloscope cannot read it, because microvolt, microampere, it will not be very much visible. It will not be clearly visible to you in the oscilloscope. So to make it clearly visible, you need instrumentation amplifier, because it will increase the gain. Instrumentation amplifier will increase the gain. So you will have a amplified output, and that is better visible on the scope. Better visible on the oscilloscope. So in the instrumentation question paper, like almost every time we see one of the question from instrumentation amplifier, because that is very important for instrumentation engineer. For EC engineer as well, we can expect some questions. So but in instrumentation question paper, we always see one of the question from instrumentation amplifier. So what is the use? Transducer will convert some form of energy to electrical signals. Now these electrical signals are of small signal. They are of some microvolt or microampere. So they are not readable. We cannot detect it. So for better detection, for make it better readable, what we need to do? We need to connect an instrumentation amplifier so that we get amplified output. So this is the use of instrumentation amplifier. It is used in a lot of sensor based industries. Okay, it is used in a lot of sensor based industries. Okay, so yeah, this is the use. What is the advantage? That also we have seen. So this is not important with respect to the gate examination, because in the written examination it is very rare that they will ask you these kind of question. But for the respect of interview, not for VLSI interviews, but in the interviews of some PSUs, these kind of questions can be asked. In PSU they can ask. VLSI, they are not going to ask these kind of question from instrumentation amplifier on all those things. They will just expect a simple analysis from you, not these kind of questions. But in the interviews of some PSUs, these kind of questions can be asked, that what are the advantage, why do we use a instrumentation amplifier, right? So let's solve a question. With that question, it will be more clear to you. If you solve this question, the use of instrumentation amplifier will be more clear to you. So this is an instrumentation amplifier, and this is working as a transducer. So we will solve this question, but let's just solve a revision question. It is very easy. So this circuit, this particular circuit is replaced by this circuit. This particular circuit is replaced by this circuit. You need to find the value of Vx and Rx. So what I am doing here, I am applying the Thevenin's theorem here. I am just finding Vth and Rth. That's it. Why I am taking this question? Because when we study OpAmp, these kind of questions, these kind of circuitry will be used a lot of time. So there I will not be telling you how I converted it to a single voltage source and single resistance. So my target is, there are two voltage sources and there are two resistance. My target is to convert it to a single voltage source and a single resistance. That's it. So what I will do, I will apply Thevenin's theorem here, right? So I am applying Thevenin's theorem here. So first I will calculate Vth. So for calculating Vth, what is Vth? Vth is open circuit voltage, that is a function of input voltage. Vth is open circuit voltage, that is a function of input voltage, that we have already studied in network analysis course. So for Vth, what you need to do, you will always open circuit the output node. I will always open circuit the output node. That means there will be 0 ampere current coming here. So I have open circuited the output node. This is V1, this is V2. What is your Vth? What will be your Vth? Can you tell me directly without even writing the nodal analysis? You can write the nodal analysis as well. Vth minus V1 by R plus Vth minus V2 by R. From Vth, is there any current coming? No. Is equals to 0. So Vth will be equals to V1 plus V2 by 2. That's it. Or I told you one method to write down. You are writing down the potential of the middle point. So what will be the potential? V1 into R plus V2 into R divided by R plus R. That would be V1 plus V2 by 2. And what about RTH? What will be your RTH? For RTH, V1 and V2 both will be shorted. This is a resistance R, this is also resistance R. And from here you need to calculate RTH. So what will be your RTH? RTH will be R by 2. Right? So this is your RTH and this is your VTH. So simply you are replacing this circuit with something like this. This R2 is there as it is. This Rx is R by 2 and this node is V1 plus V2 by 2 and this node is V naught. So in a lot of questions, what I will be doing, I will be directly replacing it like that. In a lot of question, what I will be doing, okay, from here I need to see. So I will replace, what will be this node? This node will be V1 plus V2 by 2. This is the potential, and what will be the resistance? Resistance will be R by 2. That's it. So directly I will be making this circuit. So at that time I will tell you that I have already solved a particular question on this. So you should be comfortable with these kind of analysis. So these kind of question I take just for the revision perspective, so that when I use it in the bigger circuit, you should be able to understand. Well and good. So let's solve that particular question now. So in this question, what is given is that initially your Rx was R. Initially your Rx was R. But because of some temperature changes, the Rx value becomes R plus delta R. So because of some temperature changes, this value is becoming R plus delta R. Initially it was R. Now it is becoming R plus delta R. So when it was R, when Rx value was R, what will be the output voltage? Can you tell me? First, can you write down the expression of output voltage? What is the expression of output voltage? Expression of output voltage. So what is the expression of output voltage? This ratio by this ratio, Rf by R. So R by R into 1 plus 2 times this 2R2. R2 and R2 coming 2 times. So 1 plus 2R2 divided by this resistance that is coming only for one time. That is 2R2 only. 2R2. Potential of positive. This potential. Let's just call this potential as V2 and let's just call this potential as V1. So potential of positive. This is V2, a potential of negative. V1. V2 minus V1. So V0 is basically 2 into V2 minus V1. Say yes or no. 2 into V2 minus V1. When Rx was R, when Rx is equals to R. So when Rx was equals to R, what will be this potential? Vn by 2. Say yes or no. This potential will be Vn by 2. Why so? Because there is 0 ampere current here. And also there is 0 ampere current here. So you can simply apply potential division. If this is Vn, this would have been Vn by 2. But I should not write it because this will be changing. So this is Vn by 2 and this is also Vn by 2. V1 is also Vn by 2. When Rx is equals to R, V1 and V2 both are equals to Vn by 2. That shows that your V0 will be equals to 0 volt. So basically you have made this circuit and you made sure that if the temperature changes, this resistance R will change. And you are continuously observing the output. You are continuously observing the output. So you are observing the output, okay, there is 0 volt, 0 volt. That means R is not changing. After some time, what happens is that your R changes, but you don't know your R is changing because you are only seeing the output. So what will be the output you will be getting if R changes? So R is changing by delta R. R is changing by delta R. So what will be the potential here? The potential here, V2 would become what? When Rx is R plus delta R. So what will be your V2? V2 would be R plus delta R divided by R plus delta R divided by R plus delta R, right? By R plus delta R. So it would be R plus delta R into V in, certainly into V in. R plus delta R divided by 2R plus delta R into V in. Generally this gain would be larger. Here I have taken gain equals to 2 only. So generally it would be larger, okay? So I should have made it larger because why would you take an amplifier of gain 2 only? Because you need to convert microvolt to some millivolt. So you will take a gain of at least 1000. So this should be a better gain. But in the question anything can be coming. So this is your V2 and what will be your V1? V1 will be the same. V1 will be Vn by 2 only. V1 will be Vn by 2 only because R and R. So V1 will be Vn by 2. Right? What will be your output voltage now? Output voltage is 2 into V2 minus V1. 2 into V2. What is V2? R plus delta R divided by 2R plus delta R into V in minus V in by 2. Right? Is it correct? This was your V2. This was your V1. V2 was V in by 2. And this was R plus delta R divided by 2R plus delta R. No issue about it? No issue about it. What do you see here is that what I can do 2 into 2R plus delta R. So 2R plus delta R 2R plus 2 delta R, it will be 2R plus 2 delta R. Just the calculation I am doing 2R plus 2 delta R minus 2R minus delta R into V. 2 and 2 is getting cancelled. So here what do you see? Delta R divided by 2R plus delta R into V in. This is your V naught. So here 2R will be very greater than delta R only, right? Because resistance value typically will be larger. These resistance value will be typically larger and the change will not be that much high. The change in the resistance will not be that much high. So it will be very greater than the 2R will be very greater than delta R. So what I can replace it is that V naught will be equals to delta R by 2R into V in. So what you can see, the V naught is proportional to delta R by R, right? So if because of the change in temperature your R changes, then your V0 will be proportional to the change in the delta R, right? The change in the resistance. Your V0 is proportional to the change in resistance. So your output voltage is proportional to the change in resistance. By using this configuration, which configuration? Transducer and instrumentation amplifier, you will be able to detect that there is certainly some change in the resistance because of temperature. So there is a temperature change, because of that your output voltage is changing. So you will be able to detect that there is some voltage change, there is some temperature change. So this is where we use this instrumentation amplifier. Although this question is becoming of instrumentation engineering, this question is asked in sensors as well. These kind of analysis we do for sensors and industrial instrumentation as well. When we study this subject, we will certainly do this analysis. But yeah, for now, we studied it in the amplifier only. We studied in the operational amplifier. Why so? Because it is used in sensors, right? So we just saw a simple question. We just got to know the application of this instrumentation amplifier. So there was a transducer, then there was an instrumentation amplifier, and with that the change in temperature is changing the Rx value, and the output voltage is proportional to the change in the resistance value. So that we are able to detect. Well and good. Now let's see a few more application. Very easy application. These are voltage to current converter. So there is this voltage V in. What will be your IL? So this V in will be copied here. So your V in by R is the current flowing here. The current here is V in by R, and the same current is equals to IL only. So your current is proportional to the input. So from voltage, the voltage you converted into the current, the input voltage to current converter. So at the output you are having the current that is proportional to the input. That's it. Voltage to current converter. Your voltage is being converted into the current. That's it. Very easy. The thing is, your load current, the current in this RL resistance is not depending on this resistance. The current in this RL resistance is not depending on RL. The current IL is not a function of RL. So this is what I wanted to do, that the current in load should not be the function of RL. The current in the load is function of the V in voltage. So the voltage to current converter, it is the function of input voltage, right? So very simple it is. Now current to voltage converter, so what will happen? If this node is 0, this node will also be 0, right? I should not make it ground, I should just put 0 voltage here. If this node is 0, this node will also be 0, then this node will also be 0. So the current here will be going is 0 ampere. Now this I in current is coming, Now you will say, sir, this is grounded, so complete current should go here. Is that so? That complete current should go through this short circuit path? This path is not short circuited. I told you this is virtual short. So this is just 0 voltage. That's it. You should not consider it as a ground. This is just 0 voltage. 0 voltage here, 0 voltage here. So simply there is 0 ampere current coming. So this complete I in is flowing through this RF, because this I in will be going here. Now this I in cannot go into the OpAmp, so it will be flowing through RF as well. It will be flowing through only RF. So what will be your V0? V0 will simply be minus I in into RF. Why so? Because the voltage drop will be in this direction. This voltage drop will be I in into RF. So 0 minus I in into RF. So V0 is minus I in into RF. This is your V0 is. Right? So current to voltage converter. So your V0 is depending on the input voltage. Sorry, your V0 is depending on the input current. So current to voltage converter. From current to voltage. Very easy. Very simple thing. Now we are going to see the assignment 12, but that we will see in the next video. So in this video, what we studied? We majorly studied the application of OpAmp. There are more application of OpAmp. Some application will be studied in the assignment problem only, because they are just question based. Like you saw these kind of application. No, just now you saw this application, current to voltage converter. I could have made it a question as well. Simply it is a question only. From V into IL I am getting, that's it. From current to voltage I am getting, that's it. Then first what we studied, first we started from the adder, inverting adder, non-inverting adder, inverting adder. We could see this is kind of a question only, right? 0 minus V1 by R1, 0 minus V2 by R2, 0 minus V3 by R3, 0 minus V0 by RF, right? And then we studied non-inverting adder. So here also we could find the potential of V, and then simply I could write down the potential of output. But for ease of calculation, we took the condition R1 is equals to R2 is equals to R3 is equals to R. Then this is what we were getting, 1 plus Rf by R, V1 plus V2 plus V3 by 3. This is not you need to mug up. You don't need to mug it up, because this configuration will not be used again and again. This configuration will be used as it is. It is not that this configuration will be used as it is. There will be some modification as well. But in case of differential amplifiers, these kind of configuration will be used as it is. Many times it will be used as it is. So it will be better if you remember the final expression. So what was the output voltage? Rf by R1 into potential of positive Va minus Vb, that's it. And what was the input resistance? R1 plus R2. Well and good. So what was the output? Rf by R1 Va minus Vb. Also you could derive it as well. How did you derive it? For the derivation, we applied the superposition theorem. First we consider only Va, then we consider only Vb. So considering Va, potential divider, simply the gain, R3 by R3 plus R2 into 1 plus Rf by R1 into Va. Then we consider only Vb. So for Vb, simply the gain would be minus Rf by R1 into Vb. Well and good. Then this was the conclusion, that these ratios are same. If these ratios are same, then your V0 would be Rf by R1 into Va minus Vb. Well and good. Then we studied instrumentation amplifier. So for instrumentation amplifier, it is the kind of differential amplifier only, but the output is higher, the gain is higher. So what is the gain? Rf by R1 into 1 plus 2R2 by Rg into Vy minus Vx, positive potential minus negative potential. Rf by R1 into 1 plus 2R2 by Rg, Vy minus Vx, that's it. This was your V0. And this is the conclusion we made. And what is the input impedance? Input impedance is infinity here. And it has a higher gain, and it has better control over gain. It has better control over gain. So this is what we, so higher gain, higher input impedance, and better control over gain, right? Then we saw this use of instrumentation amplifier. In transducer, the final stage is instrumentation amplifier, so that we get an amplified output, so it is better visible on the oscilloscope. So, and then we saw this simple example that I can reduce the circuit by simply applying Thevenin's theorem. So Vx is V1 plus V2 by 2 and Rx is R1 parallel R2. Then we saw this question. In this question, I got the potential of V1 and V2. Then I could write down the final output, that is R by R into 1 plus 2R2 by 2R2 into V2 minus V1. Then I could write down the potential of V2 and V1. Initially, the resistance was same, but then the resistance changed. So output also changed, but the output was proportional to the change in the resistance value. That's it. So this is the use of instrumentation amplifier. Then we saw this voltage to current converter and current to voltage converter. Now in the next video, we are going to solve an assignment. That would be a very, very easy assignment. So you should be able to solve it very, very quickly. So I can show you the questions. First question, second, third, fourth, fifth, MSQ it is, MSQ. Sixth, very easy it is. Seventh, transfer characteristic you need to draw. That's it. Okay. So these questions we are going to solve. These are very, very easy, and we will be able to solve it very, very quickly. Okay, then let's meet you in the next lecture. Thank you.